Greetings to all my tech heads out there in the KevTechify nation, and if you're new here, welcome. In this episode, we're going to look at modifying single-area OSPF version 2. We'll be discussing the Cisco OSPF cost metric, adjusting the reference bandwidth, OSPF accumulated costs, manually setting the OSPF cost value. We're going to test failover to backup routes. We'll look at the hello packet intervals. And finally, we're going to verify those hello and dead packet intervals. This episode is part of my series on enterprise networking, security, and automation. I'm Kevin here at KevTechify. Let's get this adventure started. The metric to determine the best path across the network is the lowest cost for OSPF. The lowest cost is the best path across the network. You're going to travel from LA to New York. You have the choice on two prices on a seat on an airplane to get there. One is going to cost you $1,000. One is going to cost you $500. It's the exact same seat next to each other, but one's going to cost $1,000, one's going to cost $500. Which one are you going to choose? The lowest cost. And anytime I hear anything with cost, I always think the lower the number, the better, because you don't want the high cost, you want the low cost, especially if the quality is the same on whatever you're buying. Now, the Cisco cost for the interface is inversely proportional to the bandwidth. Now, what that means here is the higher the bandwidth, the lower the cost. We want to give a high bandwidth a low cost, saying it's going to get the most traffic through there. We want our route, or we want that to be the best route. We want the 10 gig connection to be our main route versus the 1 gig connection. The calculation we use here for OSPF cost metric is the reference bandwidth. The reference bandwidth is a number that we've arbitrarily picked divided by the actual bandwidth. By default, our reference bandwidth is 10 to the 8th, 100 million. That gives us the formula down here for our cost metric for OSPF is 100 million bits per second divided by the interface bandwidth in bits per second. That will give us this cost. Now, the cost has to be an integer. That'll become important here in a second. Now, because the cost must be an integer, anything with fast Ethernet, gig Ethernet, or 10 gig are really fast connections. They're going to share the same cost. Their cost is going to be 1. Now, to give them different values, what we have to do is we have to adjust that reference bandwidth. We have to go away from our default reference bandwidth of 100 million bits per second, and we have to give it to something else. And we do that with an auto cost reference bandwidth. You manually go ahead and set our IP OSPF cost. Here's a chart that's going to help explain that. On the left side, we have our different interfaces. We have our 10 gig, our gig, our fast Ethernet, and our Ethernet. We have our reference bandwidth. That was 10 to the 8th or 100 million. So we have our reference bandwidth here. Then we divide that by the actual bandwidth in bits per second. Take 10 gigs, turn that into bits, and we get tens, thousands, millions, 10 billion bits per second. 100 million divided by 10 billion is 0.01, but we can only have an integer, so they set that as a 1 here. Gigabit is 100 million for our reference bandwidth, divide by 1 billion, that gives us 0.1, or rounding to the full integer gives us a 1 here. And then fast Ethernet is 100 million for our reference bandwidth, divide by the default bandwidth, divide by 100 million, that gives us a 1. All three of these cost the same because of that reference bandwidth. Ethernet, on the other hand, we have a 100 million for our bandwidth here, or sorry, our reference bandwidth. Our actual bandwidth is only 10 million. That gives us a cost of 10. What we can do now is adjust that reference bandwidth. The thing to note about adjusting our reference bandwidth is that it does not affect the actual bandwidth. If you change that reference bandwidth, it's not actually going to change the 10 gig connection into something else. It's still going to be that 10 gig connection. It just affects the calculations here to give us the value for our cost metric. To adjust the bandwidth, what we do is the command here is auto-cost. Then we want to set the reference bandwidth, and then we give it a value in megabits per second. Notice it's in megabits per second. Previously, anything we've done talking about cost, we've talked about bits per second, but now we're talking megabits per second. Every router in the OSPF domain has to have this new reference bandwidth set. Otherwise, the calculations, the cumulative sum of the cost are all going to be off. This value here we said is set in megabits. So for a gigabit Ethernet connection, the command would be auto-cost reference bandwidth 1000. 10 gig would be auto-cost reference 10,000. Remember, this is megabits per second right here. Megabits per second. To return the default, what you can do is auto-cost reference bandwidth of 100 megabits per second, 1 million bits per second. We're going to take the example we were just talking about a couple previous slides when we had our chart up there, but we're going to change our bandwidth here to 10 gigabits. So auto-cost reference bandwidth 10 gigabits or 10,000. Once again, remember that is equal to 10 billion bits per second. Our reference is now 10 billion bits per second. You can use the show IP OSPF interface command to verify what your current cost is. Here's the chart. We have our 4 types of interfaces. We've updated our reference bandwidth here to 10 billion. Remember, the old one was just 100 million. So that was the whole old one. That gave us the cost having 3 ones in there for 10 gig, and fast Ethernet. Now, when we go and update our reference bandwidth to 10 billion, we can divide it by the bits per second. So for 10 gig, it's 10 billion divided by 10 billion bits per second. That gives us a cost of 1. For a gigabit Ethernet connection, our reference bandwidth, once again, is 10 billion divided by a billion. That gives us a cost of 10. Fast Ethernet, 10 billion divided by 100 million, that's 100. And then for Ethernet, 10 billion divided by 10,000, that's a cost of 1,000. Now, each one of these different connections with different speeds have a different cost. Key point to remember, though, is if you do this auto cost reference bandwidth on one device, you need to do it on all of the devices in your OSPF network. OSPF accumulates the cost. OSPF accumulates the cost. Here's our network that we've talked about. This is that original network we started out with. Over here, I have the new cost for our connections using that modified reference bandwidth based upon the 10 gig Ethernet. And so the 10 gig Ethernet has a cost of 1, gigabit has a cost of 10, fast Ethernet has a cost of 100, Ethernet has a cost of 1,000. What we've done now is go ahead and put the cost on the networks on our chart. This connection here between R1 and R2, this is a gigabit Ethernet connection. If we look at our chart, That gave us a cost of 10. That's what we've put right here is our cost of 10. The connections between all of the routers are all gigabit connections. They all have a cost of 10. Loopback networks by default have a cost of 1 because they're directly connected and they're virtual. There is no routing that has to happen on those. Because of those two reasons, we have set the cost by default to 1. And we have 3 different networks here, 3 different loopback networks. Each router has one. We have set the cost as 1. When we do that, we can do a show IP route. The show IP route, we are on router 1 here. Router 1 is down here on the bottom left. We can do a show IP route and include anything that has to do with the network of 10.10.2.0. 10.10.2.0 is the network up here that goes off of R2 at the top. Now to get there, we have to go through the network that connects R1 to R2, and then we have to go on to that loopback network that comes out of the top of R2. When we look here, we have a cost of that first network between R1 and R2 as 10. And then we have a cost of 1 to get onto that loopback address. Adding up our cost, 10 plus 1 is 11 in our show IP route statement. We see that for network 10.10.2.0 with a /24, the administrative distance of trustworthiness is 110. That's the value assigned for OSPF. But notice our cost right here. Our metric is 11. That 11 comes from the cumulative cost of our networks to get from our device to the destination network. That is that 11 right there. We can also do a show IP route for just the network itself. It'll give us some information. Right here is that metric again. Metric of 11, that's that cumulative cost. Also gives us our administrative distance. That's the 110 value for OSPF. Down here, we also see again that we have the route metrics is 11. That is that cumulative cost a third time. That's where that 11 comes from, the cost of the network from R1 to R2, and then the cost to get onto that loopback 0 network, a cost of 1. If you're liking this episode on modifying single-area OSPF version 2, and you're getting value out of it, and depending upon the platform you're using, please click that like button, give a 5-star rating, leave a comment. Doing this supports the channel, which in turn helps me bring you more great content. Subscribe to my channel and click that notification bell. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. We can go and we can manually set the cost of different networks, the cost of different interfaces. Reasons you'd want to do that. You as the administrator, you want to influence that path selection. You want to use one path over another path. Maybe one path is you pay a monthly fee for the amount of data that goes through it. The other path is a path where you pay for every megabyte you send through that. And so you want to optimize that one monthly fee, send as much data across there as you can. You want to make that cost higher so it's used later. And what happens here is if we look at our diagram here, I have our diagram, and what we're going to do is we're going to increase that cost on R1. That's where we're at, is on R1. We're going to go into interface gig 00. That is the connection between R1 and R3. We're going to increase that IP OSPF cost. We're going to take it from 10. We're going to increase it to 30. We're going to go into interface loopback 0, and we're going to increase that cost from 1 to 10. And going back to the example I was just showing you, between R1 and R3, that might be that metered connection where you pay per megabyte being sent across that. Because it has a higher cost, a higher number associated with it, it's not going to have priority over the other connections. And that gives us a higher priority. But what happens when we have a failure? We've manually adjusted some of our costs on our network. We've adjusted all the loopbacks here to a cost of 10. So all three of these routers have a loopback address. We've manually set those costs to 10. We also, from that previous slide, we set the connection between R1 and R3 as a manual cost of 30. We went through and we set that. What happens when that connection between R1 and R2 goes down? You're trying to connect into this loopback network off of the top of R2 here. You're trying to connect into it. The cost to get there, that was 11. Now, because we increased that loopback network here to a manual cost of 10, that cost was 20 to get there. If we were to go from R1, R3 to R2 to get into that network up here, that would be going across this network between R1 and R3. That would be a cost of 30, plus then the cost between R1 and R2, that would be a cost of 10. And then the cost to get onto the loopback network right here, that would be another cost of 10. To get there, that would be a cost of 30 plus 10 plus 10. That would be a value of 50. When this connection between R1 and R3, that goes down, the only route to get to this loopback network off of R2 is to take the long trip R1 to R3 to R2. That's a value of 50. That network goes down. We can do a show IP route statement again. We can look in here. The IP address that we're trying to get to is 10.10.2.0. That's this network. That's the third entry down here. We can see that the administrative distance is 110. That's for OSPF, the trustworthiness. But now our metric is 50. That 50 is this cumulative value here of 30 plus 10, plus 10 from right here, plus 10 to get onto this network, the manual cost up here. That is that value. To get to network 10.10.3.0, 10.10.3.0, that's the loopback off of R3 right here. We have to go through the manual cost of 30 plus the manual cost of 10. That gives us 40. That's where this value comes from. And then to get to these other networks, the network of 10.1.1.4, which is the network that was directly connected to R1 and R2, but that connection on R1 went down. We have to go all the way through the network. We have to go from R1 to R3 to R2 onto that 10.1.1.4 network. So it's 30 plus 10 plus 10 again. That's our 50. To get to the 10.1.1.8 network, we have to go through a manual cost of 30 and then on to 40. That's where this number comes through. That's how we calculate out our best paths to get to our destinations. As we work with OSPF, we are sending out this hello packet. That's the start of figuring out what our networks look like. That's the first step in OSPF. It's also the communications that are maintained by not the DR other routers, the non-designated router, the non-backup designated router. Hellos are sent out every 10 seconds. So every 10 seconds, the router says, hello, here's my router ID. And then they hopefully do get a response back saying, yep, I'm glad to meet you. Here's my router ID. And it's sent out every 10 seconds. We send that out as a multicast on a special multicast address, 224.0.0.5. That's all OSPF routers are set up to listen to that. Hellos aren't set out on passive interfaces. Once again, a passive interface is an interface that is participating in the OSPF routing, but it doesn't need updates sent out there because that interface is not connected to another device that needs OSPF information. It's just a network that probably has devices on it, so you can set that up as a passive interface. Then we have a dead interval. This dead interval is a period that the router waits to receive a hello packet before declaring that neighbor is down. So we wait a certain amount of time. If we don't get a hello in that certain amount of time, then we say this neighbor is down. We can no longer rely on it. We can no longer send it. We're going to remove it from our routing tables. So when this expires, it gets removed from that link state database. Routers flood the link state database about the with information about that down neighbor out of all of its interfaces, and all the devices are made aware of it. By default, Cisco uses the default dead interval timer is 4 times the hello interval timer. If we take all the defaults, the hello timer is 10 seconds. We send out a hello packet every 10 seconds. The default dead interval is 4 times the hello seconds, or 4 times the hello timer, which is 10 seconds. So 4 times 10 is 40. On a completely default system, that dead interval is 40 seconds. And that goes for multi-access networks and point-to-point networks. To verify our hello and our dead interval timers, what we use here is the show IP OSPF interface command. Now, they can all be configured on a per interface basis, so each interface could have a different number. But the neighbors have to match each other. To form that adjacency, the hello timer and the dead interval timers, they need to match. So that conversation between those two, that needs to match. But for each one of those connections, you could have different values. Now, to check what the values is, we do the show IP OSP interface command, and you specify your interface. About 6 lines down here, it lists out our timer intervals. It says our hello timer is set to 10, our dead interval timer is set to 40. To see how long it's been since we received a hello statement from our neighbors, we can use the show IP OSPF neighbor command. It's going to give us the neighbor ID, which is our router ID. We are on R1. Remember, R1 had a router ID of 1.1.1.1. Router 2 had 2.2.2.2. Router 3 had 3.3.3. We can see each one of our 2 neighbors here coming across. We have a full conversation happening, but then we have our dead timer. There is 35 seconds left on this dead timer. If it was the default settings, it started at 40. We went down, so it's been 5 seconds since we've heard a hello from our neighbor at 3.3.3.3. We have 31 seconds left to hear a hello from our 2.2.2. neighbor. This is the time that is left. To modify those intervals, we use the IP OSPF, so it's part of the IP suite. We're dealing with the OSPF protocol, so we start off with IP OSPF, and then it's either hello interval or dead interval. You can use one of these 2 words, and then you specify the number of seconds there, that however long you want it to be. Once again, the default for the hello is 10. The default for the interval is 40 if you have the default for hello set at 10, because it's 4 times the hello timer. You can specify these 2. It doesn't always have to stay as 4 times the hello timer. You could specify it differently. Best practices, these are the numbers you should keep. If you try to tweak them and use different numbers and you want to revert back to the default, what we can do is put no in front of the IP OSPF hello timer. They always have to have that timer in there, but if you put no, it removes the commands you have entered in and it goes back to the default. So no IP OSPF hello interval and no IP OSPF dead interval returns them to their defaults. Here we can see we're setting the interval timers. You have to go into the interface because once again, this is interface specific. So we're going into gig 000. We enter in our command IP OSPF, and then we're going to set the hello interval to 5 seconds. So every 5 seconds, we're now going to send out a hello. Wait 5 seconds, send out another one. Send out another one. Then we're going to set our dead interval timer to 20. It just happens to be 4 times that new hello timer. It doesn't have to be, but it just happens to be there. We set it at 20 seconds. So if we don't hear anything in 20 seconds, we're going to say that that neighbor is dead to us. Go ahead, enter it in. Notice we now go through a system update saying that we went from full to down. The reason we lost adjacency is the dead interval timer. It expired, and the hello interval needs to match on both ends of that connection, on that point-to-point connection, but we haven't configured the other end of that connection. Because we haven't configured it, we haven't got our hello messages in. That interval time expired, and it drops that adjacency. We can do a show IP OSPF neighbor command here, and we can see we are no longer connected to our 2.2.2. We no longer have that adjacency to router 2. I do need to go back up here and say this for the for the dead interval timer. For the dead interval timer, when we set the hello timer to 5, it automatically set the dead interval timer to 20. The reason we entered this command in here is it will document it. It will save it in the settings. When you go back and you look at the interfaces, it will tell you what it was. If we go back and change this into 20 here, the hello timer into 20, it will automatically adjust the dead interval timer to 4 times that number. It will now set it to 80 seconds. Even if you do not put this line in and say 80, it will adjust it automatically to 80 seconds. It was my pleasure to provide you with this wonderful episode on modifying single-area OSPF version 2. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com. You can get all of these episodes in video and podcast form. In the upper right is my playlist for my series on enterprise networking, security, and automation. In the bottom right here is one of my favorite videos that I linked just for you. Thank you so much for watching this episode of my series on enterprise networking, security, and automation. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.